Let's start with something simple. You're lying there right now, maybe under a blanket, maybe with the lights off, and the room around you feels solid. The pillow under your head, the mattress beneath you, the walls, the ceiling. Everything has a certain reassuring heaviness to it. You push on something, it pushes back. You drop something, it falls. The world behaves. It follows rules you learned as a kid without anyone even having to teach you. Things are where they are. They move when you push them. They stop when something gets in the way. That's the world you know, and honestly, it's the world that every scientist knew for a very long time. Centuries, really. And then, right around the turn of the 20th century, a handful of people started noticing that when you look very, very closely at what matter is actually doing, not at the scale of baseballs and bridges, but at the scale of atoms, at the scale of light itself, the rules change, not a little, completely. And the story of how we figured that out, how we argued about it, how some of the smartest people who ever lived got it wrong and then got it right and then still couldn't agree on what it meant. That's what we're going to talk about tonight. Slowly, gently, one piece at a time. So let's go back. Let's go back to the very end of the 1800s, because that's where this story really begins, and the mood at the time is important. Physics in the late 19th century had a particular feeling to it, a kind of confidence that's hard to imagine now. If you were a physicist in, say, 1895, you had pretty good reason to feel like your field was nearly finished. Seriously. Newton had given you mechanics, the laws of motion, gravity, the whole framework for understanding why planets orbit and cannonballs arc and tides rise. James Clerk Maxwell had unified electricity and magnetism into one beautiful set of equations in the 1860s and shown that light itself was an electromagnetic wave. Thermodynamics was well understood. The periodic table was filling in nicely. There's a famous sentiment, often attributed to Lord Kelvin, William Thomson, the great British physicist, that physics was essentially complete, that all that remained were a few minor details to clean up. Whether Kelvin actually said exactly that is debated, but the attitude was real. The feeling in the air was that the big questions had been answered. The universe was a giant clockwork running on Newton's laws, and we'd more or less figured out the mechanism. Here's the thing, though. There were these little problems. Small cracks in the foundation that most people assumed would be patched up easily. And one of them, maybe the most important one, had to do with something called black body radiation. Now, that sounds technical, but the idea is actually pretty intuitive once you think about it. Imagine you have an object, any object, a piece of metal, a lump of coal, anything. When you heat it up, it starts to glow. You've seen this. Think of a stovetop burner turning red, or the filament inside an old incandescent light bulb glowing white hot. The hotter something gets, the more light it gives off, and the color of that light changes from deep red to orange to yellow to white to bluish white as the temperature climbs. A blackbody is just an idealized version of this, a perfect absorber and emitter of radiation. And physicists wanted to predict exactly how much light a blackbody would emit at each wavelength for a given temperature. Simple enough question, right? You've got Maxwell's equations, you've got thermodynamics. You should be able to calculate this. And they could, sort of. There were formulas that worked at certain wavelengths. Lord Rayleigh and James Jeans came up with an equation based on classical physics, treating light as a wave using the standard rules, and it worked beautifully for long wavelengths, for the infrared end of the spectrum. But here's where things went sideways. As you moved to shorter wavelengths, toward the ultraviolet, the Rayleigh-Jeans formula didn't just get a little wrong. It predicted that the energy radiated should increase without limit. It should go to infinity, which is obviously physically absurd. A hot object does not emit infinite energy. You would notice. This problem was dramatic enough that it got a dramatic name: the ultraviolet catastrophe. And it wasn't just a minor embarrassment. It was a fundamental failure of classical physics to describe something as basic as a hot, glowing object. Now, enter Max Planck. And I want you to know a little about Planck as a person, because it matters for understanding what he did, and, more importantly, how reluctantly he did it. Max Planck was born in 1858 in Kiel, Germany, into an academic family. His father was a law professor. His grandfather and great-grandfather had been theologians. He was a serious, careful, deeply conservative man, and I mean that in the scientific sense. He didn't want to overthrow physics. He wanted to preserve it. He was drawn to thermodynamics precisely because it felt like bedrock. Absolute, reliable, built on firm principles. When he turned his attention to the blackbody problem in the late 1890s, he wasn't trying to start a revolution. He was trying to fix an annoying discrepancy. He wanted to find the right formula, the one that matched the experimental data across all wavelengths, and he assumed it would fit neatly into the existing framework. And he did find the right formula. In October of 1900, Planck presented an equation that fit the experimental blackbody spectrum perfectly, beautifully. At every wavelength, for every temperature, his formula matched what the experimenters were measuring. But there was a catch, and it was a catch that troubled Planck deeply. To make his formula work, he had to assume something strange. He had to assume that energy wasn't continuous. Let me explain what that means. In classical physics, energy is like water flowing from a tap. You can have any amount. You can turn the tap a tiny bit and get a trickle, or open it wide and get a flood, and every amount in between is possible. Energy flows smoothly, continuously, in any quantity you like. But Planck found that to get his equation to work, he had to treat energy as if it came in discrete little packets, specific amounts. You could have 1 packet, or 2 packets, or 3, but not 1.5. It was as if the tap could only be set to certain positions. Click, 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 with nothing in between. He called these packets quanta, from the Latin word for how much. And each quantum of energy was related to the frequency of the light by a very simple formula. E equals h times F. Energy equals a constant times frequency. That constant, h, is now called Planck's constant, and it is one of the most fundamental numbers in all of physics. Its value is incredibly tiny, about 6.626 times 10 to the negative 34 joule seconds. That smallness is important, and we'll come back to it, because it's part of why quantum effects are invisible in your everyday life. But the key idea, the revolutionary idea, was quantization. Energy doesn't flow. It steps. And here's what's really fascinating about Planck. He didn't believe it. Not really. He thought of it as a mathematical trick, a clever accounting device that happened to give the right answer. He assumed that someone would eventually figure out the real reason the formula worked, and it would turn out to be something classical, something sensible. He spent years trying to derive his own result without the quantum hypothesis, trying to find a way back to the comfortable continuous world. He couldn't. Nobody could. But Planck himself never fully embraced the radical implications of what he'd done. He'd lit the fuse, but he kept hoping someone would put it out. Think about that for a second. The man who started the quantum revolution didn't want a revolution. He was a reluctant radical, a conservative thinker who stumbled onto something that would eventually demolish the classical worldview he cherished. There's something deeply human about that, about making a discovery that's bigger than you intended, bigger than you're comfortable with, and spending the rest of your career trying to reconcile yourself to it. Now, that date, December 14th, 1900, the day Planck presented the theoretical derivation of his formula to the German Physical Society, is often cited as the birthday of quantum mechanics, and it's a reasonable choice. But the truth is, in 1900, almost nobody understood the significance of what Planck had done. It was a formula. It worked. The quantum hypothesis was a peculiar assumption buried in the derivation. Most physicists noted it and moved on. The world didn't change overnight. It rarely does. The person who took Planck's idea and ran with it, who showed that quantization wasn't just a mathematical trick but something real, something physical, something that light actually does, was Albert Einstein. And this is 1905, the famous miracle year, the annus mirabilis, when Einstein, working as a patent clerk in Bern, Switzerland, published 4 papers that each would have been enough to make a career. Everyone knows about special relativity. But the paper that Einstein himself called revolutionary, his word, wasn't the relativity paper. It was his paper on the photoelectric effect. The photoelectric effect is another one of those phenomena that classical physics couldn't explain. Here's the setup. You shine light on a metal surface, and sometimes electrons come flying off. That part isn't surprising. Light carries energy. Energy knocks electrons loose. Makes sense. But the details were all wrong. Classical physics predicted that the energy of the ejected electrons should depend on the intensity of the light. Brighter light, more energy, faster electrons. But that's not what happened. What experimenters found was that the energy of the electrons depended on the color of the light, on its frequency. Blue light kicked out faster electrons than red light, regardless of brightness. And below a certain frequency, a certain color threshold that depended on the metal, no electrons came out at all, no matter how bright you made the light. You could blast a metal surface with an incredibly intense beam of red light and get nothing, then switch to a dim beam of ultraviolet, and electrons would start popping off immediately. Classical wave theory couldn't explain this. If light were a smooth, continuous wave, then a bright enough wave of any frequency should eventually deliver enough energy to knock an electron loose. It might take a moment for the energy to build up, but it should work. It didn't. Einstein's explanation was bold and simple. Light, he said, isn't just a wave. It comes in particles, in quanta of energy, just like Planck had suggested. Each particle of light, which we now call a photon, carries an energy equal to Planck's constant times the frequency of the light. When a photon hits an electron in the metal, it's an all-or-nothing transaction. The photon delivers its entire packet of energy to the electron. If that packet is big enough, if the frequency is high enough, the electron escapes. If it's not, the electron stays put, no matter how many low-energy photons you throw at it. It's like the difference between throwing 1 bowling ball at a door versus throwing 1,000 ping-pong balls. The bowling ball might knock the door down. The ping-pong balls never will, no matter how many you throw, because no single one hits hard enough. This was radical, really radical. Because Maxwell had proven, convincingly, beautifully, with decades of experimental confirmation, that light was a wave. Interference patterns, diffraction, polarization, all of it screamed wave. And now Einstein was saying light was also a particle, not instead of a wave. Also, both. And he wasn't being tentative about it. He was saying this is what light actually is. Most physicists were skeptical. Even Planck, whose work Einstein was building on, thought Einstein had gone too far. When Planck recommended Einstein for membership in the Prussian Academy of Sciences in 1913, he praised Einstein's many contributions, but added, almost apologetically, that Einstein had sometimes missed the mark in his speculations. As for example, in his hypothesis of light quanta, Planck was essentially saying, "He's brilliant, but don't hold that photon thing against him." That's how controversial the idea was, even among the people who should have been most receptive to it. But the experimental evidence kept piling up. Robert Millikan, an American physicist who actually set out to disprove Einstein's photoelectric theory, spent about a decade doing meticulous experiments and ended up confirming it in every detail. Millikan wasn't happy about it. He called Einstein's theory bold, not to say reckless, but the data was the data. Einstein's equation predicted the energy of the emitted electrons with stunning precision. In 1921, Einstein was awarded the Nobel Prize in Physics, not for relativity, which was still considered somewhat controversial, but for his explanation of the photoelectric effect. For the photon, for taking Planck's quantum idea and showing that it was real. So now we're in the early 1900s, and physics has a problem. A deep, uncomfortable problem. Light is a wave. The evidence for that is overwhelming. And light is a particle. The evidence for that is also overwhelming. Both things are true, and they seem to contradict each other. A wave spreads out, fills space, interferes with itself. A particle is a tiny localized thing that hits one spot. How can something be both? This tension, this apparent contradiction, is going to drive the next 2 decades of physics, and it's going to lead to places that nobody, not Planck, not Einstein, not anyone, could have predicted. Because the question isn't just about light. The question is about everything. And the first person to really push that idea, to suggest that this wave-particle strangeness isn't just a property of light, but a property of matter itself, was a French aristocrat with a passion for medieval history and a doctorate in physics, and his name was Louis de Broglie. And his story is one of the most unlikely in all of physics. De Broglie came from one of the oldest noble families in France. We're talking genuine aristocracy, the kind of family that had been prominent since the 17th century, with dukes and diplomats and military commanders scattered across the family tree. Louis himself was born in 1892, and he was originally drawn to the humanities. He studied history at the Sorbonne, medieval history specifically, and by all accounts he was quite good at it. He earned a degree in history before the First World War. But his older brother, Maurice, was a physicist, an experimental physicist who worked with X-rays, and Maurice's work fascinated Louis. There was something about the deep questions of physics that pulled at him, this sense that the universe had puzzles that no amount of historical research could answer. So after the war, Louis de Broglie turned to physics, and in 1924, he submitted a doctoral thesis that was, honestly, one of the most audacious things anyone had ever written. Here's what de Broglie argued. If light, which everyone had always thought was a wave, turns out to also behave like a particle, if photons are real, then why shouldn't the reverse also be true? Why shouldn't matter, which everyone had always thought was made of particles, also behave like a wave? Think about the symmetry of that for a second. Einstein had shown that waves can act like particles. De Broglie was saying, particles can act like waves. Every particle. Electrons, protons, atoms, everything. Everything in the universe has a wavelength, and he even gave you the formula. It's beautifully simple. The wavelength of any particle equals Planck's constant, that tiny number h that Planck had introduced back in 1900, divided by the particle's momentum. Momentum is just mass times velocity, so for something heavy and slow, the wavelength is unimaginably tiny. For something as light as an electron moving at typical speeds, the wavelength is small but measurable, and that distinction matters enormously because it explains why we don't notice wave behavior in everyday life. You, sitting or lying wherever you are right now, you technically have a wavelength, but your mass is so large compared to Planck's constant that your wavelength is something like 10 to the minus 35 meters. That's not just small. That's smaller than anything that has ever been or ever could be measured. It's effectively zero. So you don't diffract when you walk through a doorway. You don't interfere with yourself. Your wave nature is real but completely, utterly invisible. But an electron? An electron is tiny. Its mass is about 9 times 10 to the minus 31 kilograms. And when you work out de Broglie's formula for an electron moving at typical speeds inside an atom, you get a wavelength that's roughly the size of an atom itself. And that's not a coincidence. That's the whole point. That's why atoms work the way they do. Now, when de Broglie submitted this thesis, his examining committee didn't quite know what to make of it. The thesis was short, only about 100 pages, and the idea was so radical that the committee was genuinely uncertain whether it was brilliant or crazy. One of the examiners, Paul Langevin, was so unsure that he sent a copy to Einstein, essentially asking, "What do you think of this?" And Einstein's response was immediate and enthusiastic. He reportedly said that de Broglie had lifted a corner of the great veil. That endorsement carried enormous weight. The thesis was accepted, and de Broglie got his doctorate. And in 1929, he won the Nobel Prize for it. But here's the thing. At the time de Broglie proposed it, there was no direct experimental evidence that matter behaved like a wave. It was a theoretical prediction, an act of pure physical intuition. The confirmation came a few years later in 1927, and it came from an experiment that was, in a wonderful twist, partly accidental. Clinton Davison was an American physicist working at Bell Labs in New York. He and his colleague Lester Germer were studying how electrons scatter off the surface of nickel. They were firing a beam of electrons at a nickel target and measuring how the electrons bounced off at various angles. It was solid, careful experimental work, but nothing revolutionary, until something went wrong. Their vacuum chamber developed a leak, and the nickel target oxidized. To fix it, they heated the nickel to high temperatures to drive off the oxygen. But that heating process did something they hadn't intended. It caused the nickel to recrystallize into large, orderly crystal grains. When they resumed their experiment with this newly crystallized nickel, the results changed dramatically. Instead of the smooth, predictable scattering pattern they'd seen before, they started seeing sharp peaks and valleys in the intensity of the scattered electrons. The electrons were coming off at very specific angles, with strong signals at some angles and almost nothing at others. If you've ever seen light passing through a diffraction grating where it splits into a pattern of bright and dark bands, this was essentially the same thing. The electrons were diffracting off the crystal lattice of the nickel, and they were doing it in exactly the way you'd predict if they were waves with the wavelength de Broglie had calculated. Davison and Germer had proven that electrons are waves. Not metaphorically, not in some abstract mathematical sense. Electrons physically diffract and interfere, just like light does. Around the same time, independently, George Paget Thomson in Scotland. And yes, he was the son of J. Thomson, who had discovered the electron as a particle in 1897. George Thomson fired electrons through thin metal foils and got the same kind of diffraction patterns. The father discovered the electron as a particle. The son helped prove it was also a wave. Both of them won Nobel Prizes for it. There's something almost poetic about that. So by the late 1920s, the situation in physics was genuinely strange. Light is both a wave and a particle. Matter is both a particle and a wave. Everything is both. This isn't just a quirk of one particular phenomenon. It's a fundamental feature of reality. And the obvious question, the question that was driving physicists slightly mad, was, how do you build a coherent theory out of this? How do you write down equations that capture this dual nature? Because classical physics doesn't have room for it. In classical physics, things are either waves or particles. Period. You need something new. And that something new came together with remarkable speed between about 1925 and 1927 in what might be the most concentrated burst of genius in the history of science. Multiple people, working partly independently and partly in communication with each other, essentially invented quantum mechanics as a complete mathematical framework. And the two biggest names in that story are Werner Heisenberg and Erwin Schrödinger. Let's start with Heisenberg, because his approach came first, and because his story is honestly kind of wild. Werner Heisenberg was born in 1901 in Würzburg, Germany. He was young, astonishingly young, when he made his breakthrough. He'd studied under Arnold Sommerfeld in Munich and then worked with Max Born in Göttingen and Niels Bohr in Copenhagen. By his early 20s, he was already deeply immersed in the central problem of atomic physics. Here's what that problem looked like. Since 1913, physicists had been using a model of the atom proposed by Niels Bohr. You might remember the Bohr model from school. It's the one where electrons orbit the nucleus in neat circular paths, like tiny planets going around a sun, but only certain orbits are allowed. The electron can be in this orbit or that orbit, but not in between. When it jumps from one orbit to a lower one, it emits a photon with a very specific energy, which corresponds to a very specific color of light. And that's why atoms emit light at only certain wavelengths, those sharp spectral lines that had been cataloged for decades. The Bohr model worked beautifully for hydrogen, the simplest atom, one proton, one electron. It predicted hydrogen's spectral lines with stunning accuracy. But for anything more complex, helium, lithium, anything with more than one electron, it started to break down. The predictions didn't match the measurements. Physicists tried to patch it up, adding more rules, more conditions, more special cases, but it was becoming increasingly clear that the whole approach was fundamentally limited. The Bohr model was a transitional theory, a stepping stone. It had the right intuition. Energy is quantized. Electrons can only exist in certain states. But it was built on a classical framework, on the idea of electrons as little balls following definite paths, and that framework wasn't adequate. Heisenberg's breakthrough came in the summer of 1925, and the circumstances are famous. He was suffering from terrible hay fever. His face was so swollen he could barely see, and he retreated to Helgoland, a tiny rocky island in the North Sea, to recover. It's a barren, windswept place, and there was essentially nothing to do there except think. And think he did. What Heisenberg decided, in a move of almost reckless intellectual courage, was to throw out everything that couldn't be directly observed. You can't see an electron orbiting a nucleus. You've never watched one go around. What you can observe are the frequencies and intensities of the light that atoms emit and absorb. Those are the measurable quantities. So Heisenberg said, let's build a theory that deals only with those observable quantities. Forget about orbits. Forget about trajectories. Forget about trying to picture what the electron is doing inside the atom. Just write down mathematical relationships between the things you can actually measure. The mathematics he came up with was unfamiliar and, frankly, strange. He organized the observable quantities into arrays of numbers, grids, essentially, and discovered that when you multiplied these arrays together, the order mattered. Array A times array B did not equal array B times array A. If you've ever done basic multiplication, you know that 3 times 5 equals 5 times 3. That's the commutative property, and we take it for granted. But Heisenberg's quantities didn't commute. The order of operations changed the answer. When Heisenberg showed this to Max Born and Göttingen, Born recognized immediately what these arrays were. They were matrices, a well-established branch of mathematics that physicists hadn't had much reason to use before. Born, along with his student Pascual Jordan, helped Heisenberg formalize the theory into what became known as matrix mechanics. It was the first complete, mathematically rigorous formulation of quantum mechanics. And it worked. It could predict the spectral lines of atoms, the intensities of transitions, all the things that the Bohr model had struggled with. But here's the thing about matrix mechanics. Almost nobody liked it. Not because it was wrong, but because it was so abstract. There was nothing to visualize, no orbits, no waves, no physical picture at all. Just arrays of numbers obeying unfamiliar rules. Physicists are human beings, and human beings want to be able to picture what's happening. They want a story, an image, something they can hold in their minds. Matrix mechanics gave you the right answers, but offered no intuition about what was actually going on inside the atom. And that's exactly where Erwin Schrödinger comes in. Schrödinger was older than Heisenberg, born in 1887 in Vienna, and he was, in many ways, a very different kind of physicist. Where Heisenberg was young and radical, willing to abandon visualization entirely, Schrödinger was more traditional in temperament. He wanted a theory you could picture. He wanted waves. And in late 1925 and early 1926, working during a now legendary holiday in the Swiss Alps. And there are some colorful stories about the circumstances of that holiday that we probably shouldn't get into, but let's just say Schrödinger's personal life was, shall we say, complicated. During that retreat, he developed an entirely different formulation of quantum mechanics, one built around a wave equation. Schrödinger took de Broglie's idea that particles have wavelengths and asked, if an electron is a wave, what equation governs that wave? What's the equivalent of the equations that describe water waves, or sound waves, or electromagnetic waves? And he found it. The Schrödinger equation. It's one of the most important equations in all of physics, and it describes how a mathematical object called the wave function evolves over time. The wave function is usually written as the Greek letter psi, and it contains, in some sense, everything there is to know about a quantum system. If you know the wave function of an electron in an atom, you can calculate the probability of finding it at any particular location, the energy it has, how it will respond to external forces, everything. And when Schrödinger applied his equation to the hydrogen atom, It reproduced all the known spectral lines perfectly. It gave the same answers as Heisenberg's matrix mechanics, but in a form that felt much more natural and intuitive. You could picture the electron as a wave wrapped around the nucleus, a standing wave vibrating in 3 dimensions, and the quantization of energy emerged naturally from the requirement that the wave had to fit neatly around the atom, the same way that a guitar string can only vibrate at certain frequencies because it's fixed at both ends. Only certain wavelengths fit. Only certain energies are allowed. It was beautiful. Physicists overwhelmingly preferred Schrödinger's approach. It was familiar. It used the kind of mathematics, differential equations, calculus, that they'd been trained in. It gave you something to visualize. Schrödinger himself was delighted because he believed he'd shown that quantum mechanics was really just a new kind of wave physics, that all this talk of particles and discontinuous jumps was unnecessary, that underneath it all, the universe was smooth and continuous and wave-like. But there was a problem, a deep and unsettling problem that Schrödinger himself struggled with for the rest of his life. And the problem was this: what exactly is the wave function? What is this thing psi that his equation describes? What is it a wave of? When you have a water wave, the thing waving is water. When you have a sound wave, the thing waving is air pressure. When you have a light wave, the thing waving is the electromagnetic field. But the wave function, what's waving? Schrödinger initially hoped it represented something physical, maybe the smeared-out charge of the electron spread through space like a cloud. But that interpretation ran into serious difficulties almost immediately, and the person who proposed the interpretation that ultimately stuck, the one that most physicists use to this day, was Max Born. And Born's answer was one of those ideas that sounds simple when you say it out loud, but completely rearranges everything you thought you knew about reality. Born was a German physicist working at Göttingen, and he'd been deeply involved in the development of matrix mechanics. He was one of the 3 authors, along with Heisenberg and Pascual Jordan, of that key paper that formalized the whole framework. So he understood the mathematics of quantum mechanics from the inside. And when Schrödinger's wave equation came along, Born didn't just admire it from a distance. He started using it to solve real problems, specifically the problem of what happens when you fire an electron at an atom. Scattering problems, they're called. And as he worked through the math, he noticed something. The wave function psi, this mathematical object at the heart of Schrödinger's equation, couldn't possibly represent the physical spread of the electron itself. The numbers just didn't work out that way. When you scattered electrons off atoms, you didn't get a smeared-out blob of electron arriving everywhere at once. You got individual electrons hitting individual spots, but the pattern of where they hit, over many experiments, matched the shape of the wave function. And so Born proposed something radical. He said the wave function doesn't tell you what the electron is doing. It tells you the probability of what the electron might do. More precisely, if you take the wave function at any point in space and you square it, you take the absolute value of psi and multiply it by itself, what you get is the probability of finding the electron at that location if you look. Not the certainty, the probability. Let that sink in for a moment. This is the equation that governs everything in the quantum world, and what it's tracking isn't the electron's actual position, isn't the electron's actual trajectory. It's tracking a cloud of possibilities. The wave function is a probability wave. It's a wave of likelihood, of potential, of maybe. Now, you might be thinking, okay, But isn't that just because we don't know enough? Maybe the electron really is in one specific place, and we just haven't figured out how to calculate where yet. Maybe the probability is just reflecting our ignorance, the way that when you flip a coin, you say it's 50-50, not because the coin is genuinely undecided, but because you don't know the exact force and spin and air resistance. Maybe quantum probability is like that, just a gap in our knowledge, not a feature of reality itself. And this is where things get genuinely strange. Because the answer that quantum mechanics gives, the answer that experiment after experiment has confirmed over the past century, is no. It's not like a coin flip. The probability isn't a reflection of what we don't know. It's a reflection of what there is to know. Before you measure the electron's position, it doesn't have a definite position. It's not hiding somewhere, and we just can't see it. It genuinely, fundamentally, in some deep sense, exists in multiple possible states at once. The wave function isn't a description of our ignorance. It's a description of reality. And reality, at the quantum level, is probabilistic. Bohr published this interpretation in 1926, just months after Schrödinger's equation appeared. And here's the thing. Schrödinger hated it. Absolutely hated it. He had created this beautiful equation precisely because he wanted to get away from the discontinuous, jerky, probabilistic picture that the matrix mechanics crowd was pushing. He wanted smooth, continuous waves, real, physical waves. And now Bohr was telling him that his own equation, his greatest achievement, was fundamentally about probability, about randomness, about the universe not having definite properties until you looked. Schrödinger reportedly said that if he'd known his equation would be used this way, he would have never proposed it. He was half joking, probably, but only half. And he wasn't the only one who was uncomfortable. Einstein, who had done so much to launch quantum theory in the first place. Remember, he's the one who proposed that light comes in quanta. He's the one who endorsed de Broglie's thesis. He's the one whose photoelectric effect paper was arguably the first truly quantum idea. Einstein was deeply troubled by Bohr's probabilistic interpretation. This is where that famous line comes from, the one everyone's heard some version of. In a letter to Bohr in December 1926, Einstein wrote, in German, something that's usually translated as, God does not play dice with the universe. The actual German is, jedenfalls bin ich überzeugt, dass der nicht würfelt. At any rate, I am convinced that he does not throw dice. It's a beautiful line, and it captures Einstein's conviction that underneath the apparent randomness, there must be some deeper, deterministic reality, some hidden layer we hadn't found yet. Bohr, for his part, was patient but firm. He believed the math was telling them something true about nature, not just something true about their ignorance. And eventually, history sided with Bohr. He won the Nobel Prize for this interpretation, though not until 1954, nearly 30 years after the original paper. That delay tells you something about how controversial the idea was. So now we're in 1926, 1927, and the quantum world is in a state of creative chaos. You've got Schrödinger's wave equation and Heisenberg's matrix mechanics, which have been shown to be mathematically equivalent. They give the same answers, just in different mathematical languages. You've got Bohr's probabilistic interpretation of the wave function. And you've got a growing community of physicists who are trying to figure out what all of this means, not just mathematically, but philosophically. What does it mean for reality to be probabilistic? What does it mean to say that a particle doesn't have a definite position until you measure it? What counts as a measurement? Who's doing the measuring? And this is where Werner Heisenberg makes his second great Contribution. In 1927, he published a paper introducing what he called the uncertainty principle. And it's one of those ideas that's so famous it's seeped into everyday language. People talk about the Heisenberg uncertainty principle in contexts that have nothing to do with physics. But the actual physics is more precise and more interesting than the pop culture version. Here's what Heisenberg showed. There are certain pairs of physical properties, position and momentum are the classic example, that are fundamentally linked in a way that limits how precisely you can know both of them at the same time. The more precisely you pin down a particle's position, the less precisely you can know its momentum, and vice versa. And this isn't a limitation of your measuring equipment. It's not that your instruments aren't good enough. It's a fundamental feature of nature. The universe itself doesn't have definite values for both position and momentum simultaneously. There's a built-in fuzziness, a built-in limit to how much can be defined at once. The math is elegant. The uncertainty in position multiplied by the uncertainty in momentum is always greater than or equal to a tiny constant. Planck's constant divided by 4 pi. Remember Planck's constant from the very beginning of our story? That tiny number that Max Planck introduced in 1900 to make his radiation formula work, the one he called a mathematical trick? Here it is again, showing up as the fundamental limit on how precisely reality can be defined. It's the same constant. It keeps appearing everywhere, like a signature written into the fabric of physics. Now, let me give you an analogy for the uncertainty principle, because it's one of those things that sounds abstract until you find the right way to think about it. Imagine you have a pure musical note, a perfect sine wave, a single frequency, going on forever. If someone asks you, what's the frequency of that wave? You can answer precisely. It's exactly 440 hertz, say. Concert A. But now if someone asks, where is that wave? Well, it's everywhere. It extends infinitely in both directions. It doesn't have a location. It's spread out over all of space. Now imagine the opposite. Imagine a single sharp click, a spike, a pulse that happens at one instant in one place. You can say exactly where and when it is. But what's its frequency? Well, if you analyze a sharp click mathematically, it turns out it's made up of all frequencies at once. It doesn't have a single frequency. It's a superposition of every possible frequency blended together. So you see the trade-off. A wave with a perfectly defined frequency has no definite position. A wave with a perfectly defined position has no definite frequency. And for anything in between, a wave packet, a short burst of oscillation, there's a trade-off. The more localized it is in space, the more spread out it is in frequency, and vice versa. This isn't quantum mechanics. This is just the mathematics of waves, something that signal processing engineers and musicians and acousticians deal with every day. It's called the Fourier transform, and it's been understood since the early 1800s. What Heisenberg realized was that because quantum particles are described by wave functions, this same wave trade-off applies to them. And because of de Broglie's relation, remember, the wavelength of a particle is Planck's constant divided by its momentum. Frequency and momentum are linked. So the trade-off between position and frequency becomes a trade-off between position and momentum. The uncertainty principle isn't some mysterious quantum weirdness imposed from outside. It's a natural, inevitable consequence of the fact that matter behaves like waves. If you accept wave-particle duality, the uncertainty principle comes free. But here's what's really profound about it. It means that at the quantum level, the universe is not like a clockwork mechanism where everything has a precise state and you just need to measure carefully enough to find it. There is no precise state to find. The fuzziness is real. The indeterminacy is baked in. And this was the final piece that pushed a lot of physicists, not all of them, but a lot of them, toward a radically new way of thinking about what physics is and what it can tell us. And the person who pulled all of these threads together, Born's probability interpretation, Heisenberg's uncertainty principle, the wave-particle duality, the mathematical equivalence of the two formulations, into a single coherent philosophical framework was Niels Bohr. The same Bohr who had built that early atomic model back in 1913, the one with electrons orbiting like planets. By 1927, Bohr had moved far beyond that simple picture, and he was about to articulate something called complementarity, an idea so subtle and so slippery that physicists have been arguing about what it actually means ever since. And the place where he unveiled it, the event that became the defining moment for the philosophical foundations of quantum mechanics, was the 5th Solvay Conference, held in Brussels in October 1927. If you've ever seen that famous black and white photograph, the one with rows of serious-looking men in suits, 29 of them, 17 of whom were or would become Nobel laureates. That's the Solvay Conference. Einstein is in the front row. Bohr is there. Heisenberg, Born, Schrödinger, Dirac, Lorentz, Planck, de Broglie, Curie. It's the most extraordinary gathering of scientific talent ever assembled in one room. And what happened at that conference was not just a physics conference. It was a reckoning, a philosophical showdown disguised as a scientific meeting. And the two main characters in that showdown were Niels Bohr and Albert Einstein. Now, to understand what Bohr presented, you need to appreciate just how strange his idea of complementarity really was. And honestly, even after you hear it explained, you might find it slippery. That's okay. You're in good company. Some of the greatest physicists of the 20th century found it slippery too. Here's the core of it. Bohr said that when you're dealing with quantum objects, electrons, photons, atoms, you can set up experiments that reveal their wave nature, or you can set up experiments that reveal their particle nature, but you can never set up a single experiment that reveals both at the same time. These two descriptions are complementary. They're both necessary to give a complete picture of reality, but they're mutually exclusive in any given observation. You have to choose which question to ask, and the question you ask determines the kind of answer you get. Think about what that means for a second. It's not saying that light is really a wave and just looks like a particle sometimes. It's not saying light is really a particle and just looks like a wave sometimes. It's saying that the concepts of wave and particle are both human categories, both tools we use to describe what we observe, and neither one alone captures the full reality of what a photon is. The photon is something that doesn't have a name in everyday language. It's a quantum object, and depending on how you interact with it, it shows you one face or the other. And Bohr extended this beyond just wave-particle duality. He applied the same logic to position and momentum, the very quantities in Heisenberg's uncertainty principle. You can measure position precisely, or you can measure momentum precisely, but the experimental setups required for each are incompatible. You literally cannot do both at once, and this isn't a limitation of your equipment. It's a feature of reality itself. Now, Bohr wasn't the crispest writer. His papers on complementarity are notoriously difficult to read. He would revise sentences endlessly, agonize over every word, and still produce paragraphs that left people scratching their heads. There's a famous story, possibly apocryphal, but it captures the spirit that when Bohr gave his talk at the Solvay conference, many of the attendees weren't entirely sure what he was claiming. The ideas were that subtle, that layered, that resistant to being pinned down in simple language. But the broader package, what came to be called the Copenhagen interpretation, named after Bohr's institute in Copenhagen where so much of this thinking had developed, the broader package was clearer in its practical implications, even if its philosophical depths were murky. And the Copenhagen interpretation, in its various forms, essentially said this: quantum mechanics is a complete theory. The wave function gives you all the information there is to have about a system. When you calculate probabilities using Born's rule, those probabilities aren't reflecting your ignorance of some deeper, hidden reality. They're reflecting the actual nature of things. Before you measure, the electron doesn't have a definite position. It's not that you don't know where it is. It genuinely doesn't have one. The act of measurement forces a definite outcome, and which outcome you get is fundamentally random. That's the Copenhagen interpretation in a nutshell. And for most working physicists, it became the default, the shut up and calculate approach, as it was later somewhat unfairly characterized. You use the math, you get the predictions. The predictions match experiment to extraordinary precision, and you don't lose sleep over what the wave function really means. But Albert Einstein lost sleep over it. A lot of sleep. And this is where the Solvay conference gets really interesting, because Einstein didn't just disagree with the Copenhagen interpretation. He set out to destroy it. Not with philosophical arguments. Einstein was too good a physicist for that. He tried to destroy it with thought experiments. Clever, ingenious, carefully constructed hypothetical scenarios designed to show that quantum mechanics was either incomplete or inconsistent. The way it worked, according to several accounts, was almost like a chess match played over breakfast. Einstein would show up to the morning meal with a new thought experiment, some scenario where, he claimed, you could beat the uncertainty principle. You could measure both position and momentum simultaneously. Or you could determine which path a particle took through an interference experiment without destroying the interference pattern. Something that the Copenhagen interpretation said was impossible. And then Bohr would spend the rest of the day, sometimes agonizing over it, pacing, pulling in Heisenberg and Pauli and others to help him think it through. And by dinner, or by the next morning, Bohr would have found the flaw in Einstein's argument. Every single time. Every thought experiment Einstein proposed, Bohr found a way to show that the uncertainty principle held, that complementarity was consistent, that you couldn't sneak around the quantum limits. One of the most famous of these exchanges, and this one actually happened at the 6th Solvay conference in 1930, 3 years later, but it's so good that it belongs in this story, involved Einstein proposing a box filled with radiation. The box has a shutter controlled by a clock. At a precise moment, the shutter opens briefly and lets out a single photon. You weigh the box before and after, using Einstein's own E equals mc squared to determine the energy of the photon, and you know the exact time the shutter opened because you controlled the clock. So now you know both the energy and the time of emission precisely, which would violate the energy-time version of the uncertainty principle. It's a brilliant argument, and reportedly, Bohr was genuinely shaken by it. He couldn't find the flaw that evening. People who were there described him as going from one person to another, trying to convince them it couldn't be right, but unable to explain why. And then, overnight, Bohr found the answer. And here's the beautiful irony. He used Einstein's own general theory of relativity to do it. Bohr pointed out that when the box loses mass by emitting the photon, it rises slightly in Earth's gravitational field, Because you're weighing it. And general relativity tells us that a clock's rate depends on its position in a gravitational field. Clocks run slower in stronger gravity. So the very act of weighing the box to determine the photon's energy introduces an unavoidable uncertainty in the clock's timing. And when you work through the math carefully, the uncertainty in energy times the uncertainty in time comes out to be exactly Planck's constant. The uncertainty principle holds. Einstein was reportedly stunned. He couldn't refute it. And what makes this exchange so remarkable is that Bohr used Einstein's greatest achievement, general relativity, to defend the theory that Einstein was trying to tear down. It's one of the most dramatic moments in the history of physics. But here's the thing you need to understand about Einstein. He wasn't being stubborn or foolish. He wasn't refusing to accept quantum mechanics because he couldn't understand the math. He understood it perfectly well. His objection was deeper than that. Einstein believed, truly, passionately believed, that there was an objective physical reality out there, independent of whether anyone was looking at it. The moon is there even when nobody is observing it. Electrons have positions, even when nobody is measuring them. And a theory that says otherwise, a theory that says the act of observation creates the reality, struck Einstein as fundamentally incomplete. There must be, he felt, some deeper layer of description, some set of hidden variables that quantum mechanics was missing, and once you found them, the apparent randomness would dissolve into deterministic order, like the way the apparently random motion of pollen grains in water dissolves into the deterministic physics of molecular collisions once you understand what's really happening. And you know what? That's a perfectly reasonable philosophical position. It's not crazy. It's not anti-scientific. It's just a different set of assumptions about what a physical theory should look like. And the debate between Einstein and Bohr wasn't really about the math. They agreed on the math. It was about what the math meant, what kind of universe it described, whether probability was fundamental or a sign of ignorance, whether reality existed independently of observation. This is the kind of question that lives at the border between physics and philosophy. And reasonable, brilliant people came down on different sides. Most of the younger generation, Heisenberg, Pauli, Dirac, Jordan, sided with Bohr. They were comfortable with the new quantum worldview. But Einstein, Schrödinger, de Broglie, and later David Bohm, they never accepted it. They kept looking for alternatives, for deeper theories, for ways to restore the kind of reality that classical physics had promised. And for decades, the Copenhagen interpretation won. Not because it was proven right, but because it worked. It made predictions. Those predictions matched experiments. And nobody could come up with a viable alternative that did better. So most physicists just adopted it as the practical framework and moved on to doing calculations. But Einstein wasn't done. In 1935, 8 years after that first Solvay showdown, he and two younger colleagues, Boris Podolsky and Nathan Rosen, published a paper that would become one of the most cited, most debated, most consequential papers in the history of physics. It's known as the EPR paper, after the initials of the three authors, and it introduced an argument so subtle and so far-reaching that it took nearly 30 years before anyone figured out how to actually test it. And what it revealed when it was finally tested was something so strange that Einstein himself would have probably been deeply uncomfortable with the result. The EPR argument starts with a simple question, one that sounds almost innocent. Can two particles that once interacted continue to influence each other instantaneously, even after they've been separated by enormous distances? And to understand why Einstein thought the answer had to be no, and why quantum mechanics seemed to be saying the answer was yes, you need to think about something called entanglement. And entanglement is one of those words that gets thrown around a lot in popular science, sometimes in ways that are a little misleading. So let's really sit with it for a moment and understand what Einstein and his colleagues were actually arguing. The setup of the EPR thought experiment goes something like this. Imagine you have two particles, let's say two electrons, and they interact with each other in some way. Maybe they're produced together in the same event, so their properties are correlated by the laws of conservation. For instance, if the total spin of the system has to be zero, then if one electron is spinning one way, the other has to be spinning the opposite way. That's just conservation of angular momentum. Nothing mysterious yet. Now, let the two particles fly apart. Send them in opposite directions. Let them travel far, far away from each other, across the room, across the city, across the galaxy. It doesn't matter. According to quantum mechanics, neither particle has a definite spin direction until someone measures it. Both particles exist in a superposition of spin up and spin down. And here's the crucial part. Their spins are correlated. The moment you measure one particle and find it spinning up, you instantly know the other particle is spinning down. Instantly, no matter how far apart they are. Now, Einstein looked at this and said, okay, there are really only two possible explanations here. Either the particles already had definite spin values all along. They were determined at the moment of interaction, and we just didn't know what they were until we looked, kind of like reaching into a bag and pulling out one of a pair of gloves, where finding a left glove in one bag instantly tells you the other bag has the right glove, or the act of measuring one particle somehow instantly affects the other particle across any distance, which would be what Einstein dismissively called spooky action at a distance. And Einstein was absolutely certain that the second option was absurd. Nothing, he argued, could influence anything else faster than the speed of light. That was a bedrock principle of his own special relativity, established 30 years earlier. So the only reasonable conclusion, Einstein said, was that the particles must have had definite properties all along. The quantum mechanical description, which says they don't, must therefore be incomplete. There must be additional information, hidden variables, that quantum mechanics doesn't capture. And you know what? That argument is really, really compelling. It's logically tight. The glove analogy makes perfect intuitive sense. You open one box, you find a left glove, you know the other box has the right glove. Nobody would say that opening the first box magically transformed the second glove from some undefined glove state into a right glove. That would be crazy. The gloves were always what they were. You just didn't know until you checked. The paper was published in May 1935 in the Physical Review, and it sent shockwaves through the physics community. Bohr, by all accounts, was deeply agitated by it. He reportedly told anyone who would listen that he had to respond, that the argument was wrong, that it was based on a subtle misunderstanding. He spent weeks drafting a reply, and when it came, it was, well, let's be honest, it was hard to follow. Bohr's writing was never his strongest suit. His response essentially argued that you couldn't separate the two particles in the way Einstein wanted to, that the measurement apparatus and the system formed an indivisible whole, and that it was meaningless to talk about the properties of one particle independently of how you chose to measure the other. The two particles, once entangled, were not truly separate systems anymore, regardless of the physical distance between them. Most physicists at the time read Bohr's response, nodded, and moved on. The general feeling was that Bohr had won again, that Einstein was being stubborn, clinging to an outdated classical worldview. And for nearly 3 decades, the EPR argument was treated as more of a philosophical curiosity than a scientific challenge. It appeared in textbooks as an example of how tricky quantum mechanics could be, but it didn't change how anyone actually did physics. But here's what's really fascinating. Einstein was wrong about the conclusion. The experiments, when they were eventually done, showed that quantum mechanics was right, and the particles really don't have definite properties before measurement. But his argument wasn't wrong in the way most people assumed. He had identified something genuinely profound, genuinely strange about quantum mechanics. He had put his finger on entanglement as a feature that demanded explanation, and it took the rest of the century for physics to fully grapple with what he'd uncovered. Now, there's a beautiful footnote to 1935, because it wasn't just the EPR paper that year. Schrödinger. Remember Schrödinger, the man who gave us the wave equation? He read the EPR paper and was inspired by it. He corresponded with Einstein about it extensively, and in the process, he coined the actual term entanglement. In German, Verschränkung. He called it not one, but rather the characteristic trait of quantum mechanics, the one that enforces its entire departure from classical lines of thought. Think about that. Schrödinger, who helped build quantum mechanics, was saying that entanglement was the thing that made it truly alien. Not uncertainty, not wave-particle duality, but this strange correlation between distant particles. And in that same year, in that same burst of creative frustration, Schrödinger came up with his famous cat. You've heard of Schrödinger's cat, almost certainly. It's become one of the most famous thought experiments in all of science, and it's been turned into t-shirts and coffee mugs and internet memes and all sorts of things that would probably make Schrödinger himself a little bewildered. But the original point of the thought experiment was deadly serious, and it was meant as a criticism of quantum mechanics, not a celebration of it. Here's the setup. You put a cat in a sealed box. Inside the box, there's a tiny bit of radioactive material, a Geiger counter, a hammer, and a vial of poison. If a single atom of the radioactive material decays, and radioactive decay is a genuinely quantum process, fundamentally random, the Geiger counter detects it, triggers the hammer breaks the vial, the poison is released, and the cat dies. If no atom decays, the cat lives. You seal the box and wait 1 hour, during which there's a 50-50 chance of a decay event. Now, according to the Copenhagen interpretation, before you open the box and look, the radioactive atom is in a superposition. It has both decayed and not decayed. And since the cat's fate is linked to the atom's state, the Copenhagen interpretation seems to say that the cat is also in a superposition, simultaneously alive and dead, until you open the box and observe it. And Schrödinger's point was, that's ridiculous. Cats are not both alive and dead. The fact that quantum mechanics seems to imply this, when you scale it up to everyday objects, shows that something is missing from the theory. It was meant as a reductio ad absurdum, an argument that takes a premise to its logical extreme to show that the premise must be flawed. And yet, here's the delicious irony. Quantum mechanics handled this challenge the same way it handled all the others, by being right. As experiments got more sophisticated over the following decades, physicists demonstrated superposition in larger and larger systems. Not cats, mind you. We're talking about molecules, tiny mechanical oscillators, superconducting circuits. But the principle held. Quantum superposition doesn't just disappear at some arbitrary size threshold. The reason we don't see cats in superposition isn't that quantum mechanics breaks down at large scales. It's that large, warm, complex objects interact with their environment so rapidly and so thoroughly that superposition effectively vanishes almost instantaneously. This process has a name: decoherence. And understanding decoherence would become one of the major achievements of late 20th century physics. But we'll come back to that. So by the end of 1935, the battle lines were drawn. On one side, Bohr and the Copenhagen School, saying quantum mechanics is complete. Probabilities are fundamental. Live with it. On the other side, Einstein and Schrödinger, saying something is missing. There must be a deeper reality underneath. And for a long time, decades, the Copenhagen side dominated, not because the debate was settled, but because there didn't seem to be any way to experimentally distinguish between the two positions. If hidden variables existed but gave the same predictions as quantum mechanics, how could you tell the difference? It seemed like a purely philosophical question, the kind of thing physicists could safely ignore while getting on with practical work. And there was a lot of practical work to get on with. The late 1930s and 1940s were, of course, dominated by the Second World War, and quantum mechanics went from being an abstract theoretical framework to a tool of enormous practical and terrible power. The Manhattan Project, the development of the atomic bomb, was quantum mechanics made tangible. The physics of nuclear fission, the behavior of neutrons in a chain reaction, the critical mass calculations, all of it depended on quantum mechanical principles. Many of the same physicists who had been debating the meaning of wave functions in the 1920s were now using those wave functions to design weapons of unprecedented destructive force. Heisenberg led Germany's nuclear research program. Bohr, who was half Jewish, escaped occupied Denmark in 1943 and eventually contributed to the Allied effort. The war scattered the quantum community and changed it forever. After the war, physics entered a new era. Quantum electrodynamics, QED, was developed by Richard Feynman, Julian Schwinger, and Shinichiro Tominaga in the late 1940s, and it became the most precisely tested theory in the history of science. QED described how light and matter interact at the quantum level, and its predictions matched experiments to 10 decimal places. 10 decimal places. That's like predicting the distance from New York to Los Angeles and being accurate to the width of a human hair. Feynman, in particular, brought a whole new way of thinking about quantum mechanics, his path integral formulation, where a particle doesn't take one path from point A to point B, but rather takes every possible path simultaneously, and you add up all the contributions to get the probability. It sounds insane, but it works beautifully. And Feynman had this wonderful attitude toward the interpretation question. He basically said, "Don't worry about what it means, just calculate." "Shut up and calculate" became an informal motto for a whole generation of physicists. And honestly, it was a productive attitude. The calculations worked, the technology followed. Transistors, lasers, semiconductors, nuclear power, MRI machines, all of it built on quantum mechanics, all of it functioning exactly as the theory predicted. You didn't need to know whether the wave function was real or just a mathematical tool to design a transistor. You just needed the math. But the interpretation question didn't go away. It just went underground for a while. And the person who brought it roaring back, who showed that Einstein's philosophical objection could actually be turned into a real, testable, experimental question, was a physicist from Northern Ireland named John Stuart Bell. And what Bell did in 1964 working alone at CERN during a sabbatical year, was so elegant and so profound that it's been called the most important result in the history of quantum foundations. He found a way to distinguish between Einstein's hidden variables and quantum mechanics. He found a way to actually test whether the universe was locally real. And the tool he used was a mathematical inequality, a simple, almost shockingly simple, mathematical inequality. Here's how to think about it. Remember the EPR argument. Einstein, Podolsky, and Rosen said, look, if two particles are entangled and you measure one, you instantly know something about the other, no matter how far apart they are. And Einstein said, that's absurd. That can't involve any real influence traveling faster than light. So the particles must have carried hidden instructions with them all along. Like the gloves in the box. You open one box in Paris, see a left glove, and you know the one in Tokyo is a right glove. No spooky action needed. The information was there the whole time, baked into the system from the moment the gloves were separated. And for nearly 30 years, most physicists treated this as a purely philosophical disagreement. You couldn't design an experiment to tell the difference between the particles had definite properties all along that we just didn't know, and the particles genuinely didn't have definite properties until one was measured. Both stories predicted the same measurement outcomes for the simple cases people had considered. It seemed like a question you could argue about over coffee but never actually resolve. What Bell realized, and this is the stroke of genius, is that the two stories don't always predict the same thing. If you're clever about which measurements you choose to make, and especially if you measure the two entangled particles along different angles, not the same angle, then the predictions diverge. Hidden variable theories that respect locality, meaning no faster-than-light influence, are constrained in a way that quantum mechanics is not. Let me try to make this concrete. Imagine you and a friend each receive one particle from an entangled pair. You're far apart. Different rooms, different cities, doesn't matter. Each of you has a detector, and you can set your detector to measure along one of several angles. Let's say you each independently and randomly choose one of three settings, call them A, B, and C. You both measure, you write down your results, and later you compare notes. Now, if Einstein was right, if each particle carried a hidden instruction sheet that predetermined what result it would give for every possible detector setting, then there's a mathematical limit on how correlated your results can be across different combinations of settings. Bell worked this out precisely. The correlations between your measurements, when you average over many, many trials, are bounded by a specific number. That's Bell's inequality. Any local hidden variable theory, any theory where the particles have predetermined properties and no faster than light communication happens, must obey that bound. But here's the thing. Quantum mechanics predicts correlations that violate that bound. Quantum mechanics says the correlations between entangled particles are stronger than any local hidden variable theory can produce, not by a huge amount, but by a clear, measurable amount. And that difference, that gap between what hidden variables allow and what quantum mechanics predicts, is what makes the whole thing experimentally testable. Think about what that means. Bell took a 30-year-old philosophical debate and turned it into a number. A number you could go into a lab and measure. Either the correlations in your experiment stay within Bell's bound, in which case Einstein was right and quantum mechanics is incomplete, or they exceed the bound, in which case local hidden variables are ruled out and something genuinely strange is happening. There's no wiggle room. It's one or the other. Bell published his result in 1964 in a relatively obscure journal called Physics, which actually folded not long after. The paper almost disappeared. It wasn't widely read at first. The theoretical physics community was busy with other things. Particle physics was booming, quarks had just been proposed, there was a lot going on, and Bell himself was modest about it, almost diffident. He kept working on particle physics at CERN, his day job, and pursued quantum foundations mostly on the side because it wasn't considered a serious career path. You could wreck your reputation worrying about the foundations of quantum mechanics in the 1960s. It was seen as philosophy, not physics. But a few people noticed, and they started thinking about how to actually do the experiment. The first serious attempt came from John Clauser, an American physicist who stumbled across Bell's paper as a graduate student at Columbia in the late 1960s. Clauser was immediately captivated. He could see that this was experimentally feasible. You could do this with photons, with polarization measurements, with technology that already existed or was close to existing. But when he told his thesis advisor he wanted to test Bell's inequality, the response was essentially, why? Everyone knows quantum mechanics is right. You're wasting your time. Clauser did it anyway. He teamed up with Stuart Friedman at Berkeley, and in 1972 they performed the first real experimental test of Bell's inequality. They used entangled photons produced by exciting calcium atoms, measured the polarizations at different angles, collected the statistics, and compared the correlations to Bell's bound. The result? The correlations violated Bell's inequality. Quantum mechanics won. The universe was not locally real in the way Einstein had hoped. But, and this is important, the experiment had loopholes. Technical limitations that left room for a determined skeptic to argue that maybe, just maybe, the result wasn't definitive. The biggest loophole was this. The detector settings in Clauser and Friedman's experiment were fixed in advance. They didn't change the angles during the experiment. So in principle, you could imagine some exotic hidden variable theory where the particles somehow knew what settings the detectors were going to use and adjusted their behavior accordingly. It sounds conspiratorial, and it is, but if you're trying to prove something as fundamental as the non-locality of nature, you want to close every possible loophole. And that's where Alain Aspect comes in. Aspect was a French physicist at the University of Paris South in Orsay, and in the early 1980s he designed a much more sophisticated version of the experiment. His key innovation was switching the detector settings while the photons were already in flight. The photons leave the source, they're heading toward the detectors, and while they're traveling, the detector settings are changed randomly. This means that even if you imagined some signal traveling between the two detectors, it couldn't travel fast enough. It would have to go faster than light to carry the information about the setting change from one detector to the other in time to affect the result. Aspect's experiments, published in 1981 and 1982, were a landmark. The results again violated Bell's inequality, this time with the locality loophole substantially closed. The correlations were exactly what quantum mechanics predicted, and they exceeded what any local hidden variable theory could account for. The physics community started paying much more serious attention. But even Aspect's experiments weren't perfectly loophole-free. There was still the detection loophole. Not every photon pair was actually detected, and in principle, maybe the ones that were detected were a biased sample. Maybe if you could detect every single pair, the statistics would come out differently. Again, this sounds like grasping at straws, and most physicists thought so too. But science at this level demands rigor. Over the next few decades, experimenters around the world worked to close every conceivable loophole. Better photon sources, faster random number generators, longer distances between detectors. In 2015, A team led by Ronald Hansen at Delft University of Technology in the Netherlands performed what's often called the first loophole-free Bell test. They used entangled electrons in diamond nitrogen vacancy centers separated by over a kilometer, with random setting choices made while the particles were in flight and with detection efficiency high enough to close the detection loophole simultaneously. The result, once again, was a clear violation of Bell's inequality. That same year, two other groups, one in Vienna led by Anton Zeilinger and one at NIST in Boulder, Colorado, independently performed their own loophole-free tests with entangled photons. All three experiments agreed. Bell's inequality is violated. Local realism is ruled out. So let's sit with that for a moment. What does it actually mean to say the universe is not locally real? It means at least one of two deeply intuitive assumptions about the world is wrong. Either locality is wrong, meaning things can influence each other instantaneously across arbitrary distances, or realism is wrong, meaning particles don't have definite properties until they're measured, or possibly both are wrong. But you can't have both be true. That's what Bell proved, and that's what the experiments confirmed. Most physicists, following the Copenhagen tradition, give up realism. They say the particle genuinely doesn't have a definite polarization until you measure it. The measurement doesn't reveal a pre-existing fact. It creates the fact. And the entangled partner's state is instantaneously affected, not because a signal travels between them, but because they were never really separate systems to begin with. They're one quantum system described by one wave function, and measuring part of it updates the whole thing at once. And here's something that might ease the strangeness a little, or might make it stranger, depending on how you think about it. You can't use entanglement to send information faster than light. Even though the correlations are non-local, you can't exploit them for communication. When you measure your particle, you get a random result. It's random to you. Your friend, measuring their particle far away, also gets a random result. It's only when you later compare your results that you see the correlations are stronger than any local theory allows. The randomness acts as a kind of shield, preventing faster-than-light signaling while still allowing these eerie correlations to exist. Einstein's relativity is safe in the sense that no usable information travels faster than light. But the correlations themselves are genuinely non-local. The universe is stranger than Einstein wanted it to be, but not so strange that it breaks causality. John Bell died in 1990 of a cerebral hemorrhage at only 62. He was widely expected to receive the Nobel Prize, and many physicists believe he would have if he'd lived longer. The 2022 Nobel Prize in Physics was awarded to Aspect, Clauser, and Zeilinger, the three experimentalists who tested his inequality. And the Nobel Committee explicitly cited Bell's theoretical work as the foundation. It was, in a sense, Bell's Nobel too, awarded 3 decades too late for him to hold it. Now, the violation of Bell's inequality didn't just settle a philosophical argument. It opened the door to something entirely practical, something that's reshaping technology right now. Because once you accept that entanglement is real, that these non-local correlations genuinely exist in nature, you start asking a different question. Can we use them? Can we build things with them? And the answer, it turns out, is yes. The field that grew out of this realization has a name you've almost certainly heard: quantum computing. And the story of how we got from Bell's abstract inequality to actual quantum machines sitting in labs and data centers today starts with a physicist who had an even wilder idea about what computation could be. Richard Feynman. Of course it's Feynman. The man keeps showing up in this story, doesn't he? And this time, In 1981, he's standing in front of a room full of physicists and computer scientists at MIT at a conference on the physics of computation, and he's asking a question that sounds almost too simple. He says, "Look, can we simulate a quantum mechanical system on a classical computer?" And then he answers his own question. No, we can't. Not efficiently. Here's why that matters. Think about what a classical computer does. It stores information in bits, zeros and ones, and it processes them one step at a time, or maybe a few steps in parallel if you've got a fancy machine. Now imagine you want to simulate a quantum system. Say you've got 50 particles, and each one can be in a superposition of two states. To describe the full quantum state of that system, you need to keep track of all the possible combinations of those 50 particles being in one state or the other. And the number of combinations is 2 to the power of 50. That's over a quadrillion. For just 50 particles. Add one more particle and the number doubles. Add 10 more and it increases by a factor of 1,000. The amount of information you need to track grows exponentially with the number of particles. Feynman saw this and realized something profound. Nature, he said, is doing this calculation effortlessly. Every atom in your body is a quantum system interacting with other quantum systems, and the universe somehow keeps track of all of it in real time. So maybe, Feynman suggested, instead of trying to simulate quantum physics on a classical computer, which is like trying to describe a symphony by writing out every air molecule's position, you should build a computer that itself runs on quantum mechanics. Use quantum systems to simulate quantum systems. Fight fire with fire. Now, Feynman didn't lay out a detailed blueprint. He was doing what Feynman always did. He was pointing at the horizon and saying, "There's something incredible over there. Somebody should go look." But the idea sat there, quietly radical for a few years. And then, in 1985, a physicist at Oxford named David Deutsch took it further. Deutsch is a fascinating character, deeply philosophical, one of the founders of the many worlds interpretation camp, and absolutely convinced that quantum mechanics is telling us something fundamental about the nature of reality. He proposed the idea of a universal quantum computer, a quantum machine that could, in principle, simulate any physical system, not just quantum systems, but anything. And he showed that such a machine would be fundamentally more powerful than any classical computer for certain kinds of problems. But here's the thing. For about a decade after Deutsch's paper, quantum computing was mostly a theoretical curiosity. People thought it was interesting, sure, but nobody had a killer application. Nobody could point to a specific problem and say, "Here, a quantum computer would destroy a classical computer at this particular task." It was a solution looking for a problem. That changed in 1994, and it changed because of a mathematician at Bell Labs named Peter Shor. Shor figured out an algorithm, a set of instructions for a quantum computer that could factor large numbers exponentially faster than any known classical algorithm. Now, that might sound abstract, like, who cares about factoring numbers? But think about what that means. The entire security infrastructure of the internet, your bank account, your emails, your medical records, every encrypted message you've ever sent, almost all of it relies on a mathematical assumption that factoring very large numbers is practically impossible for classical computers. Your encryption works because even the fastest supercomputer would take longer than the age of the universe to factor the huge numbers involved. Shor's algorithm said that a sufficiently powerful quantum computer could do it in hours, maybe minutes. That got people's attention. Suddenly, quantum computing wasn't just a physics curiosity. It was a potential threat to global security and also a potential tool of unimaginable power. Governments started paying attention, funding started flowing, and the race was on to actually build one of these things. But building a quantum computer, actually building one, turns out to be one of the hardest engineering challenges humanity has ever attempted. And to understand why, you need to understand what a quantum bit is, a qubit, and why it's so different from a classical bit. A classical bit is simple. It's either 0 or 1. A switch that's either off or on. A qubit, on the other hand, can be in a superposition of 0 and 1 simultaneously. Remember superposition from earlier in our story. How a quantum particle doesn't have a definite state until you measure it. A qubit exploits exactly that. Before you measure it, it exists in some combination of 0 and 1, described by probability amplitudes. And when you have two qubits, they can be entangled. There's that word again. So that the state of one is correlated with the state of the other in ways that have no classical equivalent. This is where the power comes from. With two classical bits, you can represent one of four possible states at any given moment: 0, 0, 0, 1, 1, 0, or 1, 1. But two entangled qubits can exist in a superposition of all four states simultaneously. 3 qubits can represent 8 states at once. 50 qubits can represent over a quadrillion states simultaneously. And a quantum algorithm can manipulate all of those states at the same time, performing a kind of massive parallel computation that no classical computer can match. But, and this is a huge but, there's a catch. Superposition is incredibly fragile. The moment a qubit interacts with its environment in an uncontrolled way, a stray photon hits it, a vibration jiggles it, even thermal noise from being slightly too warm, the superposition collapses. The qubit decoheres and your quantum information is destroyed. This is called decoherence, and it's the central enemy of quantum computing. Think of it this way. Imagine you're trying to balance a coin on its edge. That's your qubit in superposition, not heads, not tails, but something in between. Now imagine you're trying to do this not on a table, but on the deck of a ship in a storm. Every tiny vibration, every gust of wind knocks the coin over. That's decoherence. And to make a useful quantum computer, you need to keep not just one coin balanced, but hundreds or thousands of them, all at the same time, all while performing precise operations on them. This is why the engineering is so extreme. Most leading quantum computers today use superconducting qubits, tiny circuits made of superconducting metal, cooled to temperatures colder than outer space. We're talking about 15 millikelvin. That's 15 thousandths of a degree above absolute zero. The dilution refrigerators that cool these machines are extraordinary pieces of engineering in their own right. Nested chambers that use mixtures of helium-3 and helium-4 to reach temperatures that essentially don't exist anywhere in the natural universe. Deep space, the cosmic microwave background, is about 2.7 Kelvin. These machines operate at a temperature roughly 200 times colder than that. And even with all that cooling, even with all that isolation, qubits still decohere. Current superconducting qubits maintain their quantum states for maybe a few hundred microseconds at best. That's not a lot of time. Every quantum operation you perform has to happen within that window, and every operation introduces a small probability of error. So you're in a race. You need to perform your computation before the qubits lose their quantumness, and you need to do it accurately enough that the errors don't swamp your answer. This is where quantum error correction comes in, and it's one of the most beautiful and maddening aspects of the whole field. The basic idea, proposed in the mid-1990s by Bohr himself and independently by Andrew Steen at Oxford, is that you can encode a single logical qubit, the qubit you actually want to compute with, across many physical qubits. If some of the physical qubits decohere or pick up errors, the redundancy lets you detect and correct those errors without destroying the quantum information. It's conceptually similar to classical error correction, but it's far more difficult because of a fundamental constraint. You can't just copy a qubit. There's a result called the no-cloning theorem, proved by Wouters and Zurek in 1982, which says it's physically impossible to make an exact copy of an unknown quantum state. So quantum error correction has to work without copying, using entanglement to spread information across qubits in clever ways. The upshot is that to get one reliable logical qubit, you might need 1,000 or more physical qubits. And to run Shor's algorithm on a number large enough to break real-world encryption, you'd need several thousand logical qubits, which means millions of physical qubits. Current machines have a few hundred to maybe a little over 1,000 physical qubits, so we're not there yet. Not even close in some sense. But the progress has been remarkable. In 2019, Google's quantum computing team, led by John Martinis, announced that their 53-qubit processor, called Sycamore, had achieved what they called quantum supremacy. It performed a specific calculation in about 200 seconds that they estimated would take the world's fastest classical supercomputer 10,000 years. Now, IBM pushed back on that claim, arguing that with clever classical techniques, the supercomputer could do it in a matter of days, not 10,000 years, and the task itself was somewhat artificial. It was designed to be easy for a quantum computer and hard for a classical one, not something practically useful. But even the skeptics acknowledged it was a milestone. For the first time, a quantum machine had done something that was at least arguably beyond classical reach. And quantum computing isn't the only technology that grew out of our understanding of entanglement and quantum weirdness. There's quantum cryptography, specifically quantum key distribution, which uses the principles of quantum measurement to create communication channels that are theoretically impossible to eavesdrop on without detection. The idea goes back to Charles Bennett and Gilles Brassard in 1984, and it's already being deployed in real networks. China launched a quantum communication satellite called Mesius in 2016 and demonstrated entanglement-based key distribution over distances of more than 1,000 kilometers. There's quantum sensing, which exploits the extreme sensitivity of quantum states to build instruments of extraordinary precision. Atomic clocks so accurate they won't lose a second in billions of years. Magnetometers sensitive enough to detect the faint magnetic fields produced by neural activity in the brain. Gravimeters that can map underground structures from the surface. All of these technologies trace their lineage back through the same story we've been following all night. Planck's desperate hypothesis. Einstein's stubborn photon. Bohr and Heisenberg arguing in Copenhagen. Schrödinger's cat, neither alive nor dead. Bell's elegant inequality. Aspect's photons flying through the basement of a lab in Orsay. Each piece built on the last. Each breakthrough opening doors that the previous generation couldn't even see. And yet, for all this technological progress, the deepest question remains stubbornly unanswered. We can build quantum computers. We can harness entanglement. We can predict experimental outcomes to 12 decimal places. But we still don't agree on what quantum mechanics actually means. What is really happening when a particle is in superposition? What is the wave function, really? Is it a real thing out there in the world, or just a mathematical tool for calculating probabilities? And that question, the interpretation question, has never gone away. It's been simmering underneath everything, From the very beginning, and in the decades since Bell, it's only gotten louder, more serious, more philosophically sophisticated, and honestly, more fascinating than ever. For decades, if you were a working physicist and you started asking questions like, but what does the wave function really represent? You'd get a polite but firm nudge to stop wasting everyone's time. The Copenhagen interpretation, Bohr's framework, the one that said you shouldn't ask what's happening between measurements, that the math gives you probabilities and that's all you need, had hardened into something close to orthodoxy. Not because everyone was truly satisfied with it, but because it worked. It worked spectacularly well. And there was real physics to do, real calculations to run, real experiments to design. So the interpretation question got pushed to the margins. It became, in many departments, a career risk. You could think about it privately, maybe over a beer, but you didn't publish papers about it if you wanted tenure. But here's the thing about genuinely deep questions. They don't go away just because you ignore them. And starting in the 1950s and accelerating after Bell, a handful of physicists kept pushing, kept proposing alternatives, kept insisting that shut up and calculate wasn't good enough. And what they came up with is genuinely wild. So let's walk through a few of these interpretations, not because any of them is definitively right. Nobody knows which one is right, and that's kind of the whole point. But because each one reveals something different about what quantum mechanics might be telling us about the nature of reality. And honestly, they're just beautiful to think about as you're lying here in the dark. The first big alternative came from a young American physicist named Hugh Everett III, and it arrived in 1957, right in the middle of the don't ask questions era. Everett was a graduate student at Princeton working under John Wheeler, the same Wheeler who had worked on the Manhattan Project, who coined the term black hole, who was one of the most creative and wide-ranging minds in 20th century physics. And Everett looked at the measurement problem, that strange discontinuity where the wave function supposedly collapses when you observe it. And he said, what if it doesn't collapse? What if the wave function is real and it never collapses? And what actually happens is that every possible outcome occurs, but in separate, non-communicating branches of reality. Let that settle for a moment, because this is the many worlds interpretation, and it is exactly as dramatic as it sounds. When you measure a particle that's in a superposition of spin up and spin down, you don't get one result while the other possibility vanishes. Instead, the universe branches. In one branch, you see spin up. In another branch, an equally real copy of you sees spin down. Both outcomes happen. Both versions of you are real. They just can't talk to each other anymore because they've decohered. They've become entangled with their environments in incompatible ways, like two radio stations drifting to different frequencies until neither can pick up the other's signal. Now, your immediate reaction might be, that's insane. That's the most extravagant ontological proposal in the history of human thought. And you'd be right, in a way. It posits an essentially infinite number of branching universes, constantly multiplying with every quantum event, everywhere, all the time. The sheer profligacy of it is staggering. But here's what Everett would tell you, and what modern proponents like David Deutsch and Sean Carroll would tell you. The math doesn't change. Not one equation is different. All Everett did was take the Schrödinger equation seriously and refuse to add the collapse postulate. He said, what if the math is the whole story? What if the wave function is all there is, and it just evolves according to Schrödinger's equation, forever, without exception? And when you follow that logic, you get many worlds. You get branching. You don't add anything to the theory. you actually subtract something, the collapse rule, and you end up with this enormous, extravagant-looking conclusion. It's a case where the simpler theory, in terms of its fundamental rules, gives you the more complex-looking reality. Everett's thesis was largely ignored when it was published. Wheeler supported him, but couldn't really protect the work from the prevailing Copenhagen consensus. Everett left physics entirely, went into defense analysis and operations research, and never returned to academic physics. He died in 1982, at just 51, having never seen his interpretation taken seriously by the mainstream. It's one of those quiet tragedies of science, a genuinely original thinker who was ahead of his time and paid the professional price for it. But many worlds didn't die with Everett's career. It kept finding advocates, kept gaining traction, especially as decoherence theory developed in the 1970s and 80s and provided a mechanism for understanding why the branches don't interfere with each other. The physicist Wojciech Zurek and others showed that when a quantum system interacts with a complex environment, air molecules, photons, the particles in a measuring device, the different components of the superposition become effectively isolated from each other, not because of any collapse, but because of the sheer complexity of the entanglement. It's like dropping a single drop of ink into the ocean. The ink is still there, technically, but it's spread so thin and mixed so thoroughly that you could never gather it back. Decoherence explains why the world looks classical to us even if the underlying reality is quantum all the way down. And it works within many worlds beautifully. It's the mechanism that makes the branches effectively separate. Today, many worlds is probably the second most popular interpretation among physicists, and in some subfields, quantum computing, quantum cosmology, it might actually be the most popular. But it's not the only game in town. There's another approach that takes a completely different path, and it goes back even further. To 1927, actually, and to Louis de Broglie, the same French prince who proposed matter waves. De Broglie suggested that particles are real, definite things with real, definite positions at all times, but they're guided by the wave function, which acts as a kind of pilot wave, steering the particle along its path. The particle surfs the wave, so to speak. The wave is real, the particle is real, and together they produce all the quantum phenomena we observe. Interference, diffraction, everything. De Broglie presented this idea at the 1927 Solvay conference, and it was essentially demolished by the assembled heavyweights, particularly by Pauli, who raised a technical objection that de Broglie couldn't answer at the time. The idea lay dormant for a quarter century until David Bohm, an American physicist with a remarkable and turbulent life story, independently rediscovered and extended it in 1952. Bohm had been a protege of Robert Oppenheimer at Berkeley, but during the McCarthy era, he was hauled before the House Un-American Activities Committee, refused to testify against colleagues, lost his position at Princeton, and eventually left the United States entirely, spending years in Brazil, then Israel, then finally settling in London. It was during this period of exile and intellectual independence that he developed what's now called Bohmian mechanics, or the de Broglie-Bohm theory. In Bohm's version, particles always have definite positions. There's no superposition of locations. The electron is always somewhere specific, but there's also a wave function, and it's real, and it guides the particle's motion through a precise mathematical rule called the guiding equation. The wave function evolves according to Schrödinger's equation, just like in standard quantum mechanics, and the particle follows along, its trajectory shaped by the wave. When you do the double-slit experiment in this picture, The particle goes through one slit. It always goes through one slit. But the wave goes through both. And the wave on the other side creates an interference pattern that guides the particle to land in the right places. You get the interference pattern, not because the particle went through both slits, but because the guiding wave did. It's deterministic. Given the initial position of the particle and the initial wave function, the future is completely determined. The apparent randomness of quantum mechanics arises because we don't know the initial positions precisely. They're distributed according to the Born rule, and once that's the case, they stay distributed that way. So the probabilities aren't fundamental. They're just a reflection of our ignorance, like in classical statistical mechanics. And here's what's really interesting. Bohmian mechanics reproduces every prediction of standard quantum mechanics. Every single one. The experiments can't tell the two apart. It's a fully deterministic, realistic theory that gives you all the same numbers. So why isn't everyone a Bohmian? Well, there are costs. The theory is explicitly non-local. The guiding wave connects distant particles instantaneously, which is how it handles entanglement. And when you try to extend it to relativistic quantum field theory, things get complicated and somewhat awkward. Many physicists find it inelegant or feel that it adds structure, those definite particle positions, without adding any new predictions. But it exists, it works, and it shows that the no hidden variables claims you sometimes hear are too strong. What Bell proved is that no local hidden variable theory can work. Bohm's theory is non-local, and it's perfectly consistent with Bell's results. And then there are other approaches, each with its own flavor. There's the consistent histories interpretation, developed by Robert Griffiths and refined by Murray Gell-Mann and James Hartlell, which tries to make sense of quantum mechanics without either collapse or many worlds, by carefully defining which sets of historical narratives are logically consistent. There's cubism, quantum Bayesianism, championed by Christopher Fuchs and others, which takes the radical position that the wave function doesn't describe the physical world at all, but rather an agent's personal beliefs about what they'll experience. In cubism, quantum mechanics is a tool for navigating an irreducibly participatory universe, and the mystery of measurement dissolves because measurement is just an agent updating their expectations. It's provocative, philosophically sophisticated, and deeply polarizing. There are objective collapse theories, like the one proposed by Giancarlo Ghirardi, Alberto Rimini, and Tullio Weber in 1986, the GRW theory, which modifies the Schrödinger equation slightly, adding a tiny, random, spontaneous collapse mechanism. For a single particle, the collapses are so rare you'd never notice, maybe once every 100 million years. But for a macroscopic object made of trillions upon trillions of particles, at least one of them is collapsing at any given moment, and because they're all entangled with each other, that single collapse drags the whole object into a definite state. It's an elegant idea, because it explains why big things behave classically and small things behave quantum mechanically, and it does so with a concrete physical mechanism rather than a vague philosophical prescription. The catch is that it's a genuinely different theory from standard quantum mechanics. It makes slightly different predictions, and people are actively looking for ways to test it. And that's maybe the most exciting thing about the interpretation question right now. It's no longer purely philosophical. Some of these interpretations, particularly objective collapse theories, make predictions that differ ever so slightly from standard quantum mechanics. If you could build sensitive enough experiments, you could potentially rule some of them out. There are proposals involving massive superpositions, putting larger and larger objects into quantum superposition and seeing whether they collapse spontaneously, as GRW predicts, or stay coherent, as many worlds and Bohmian mechanics predict. The technology isn't quite there yet, but it's getting closer. We're talking about superpositions of objects with millions of atoms, maybe more. It's an extraordinary experimental frontier. So where does all of this leave us? You've been lying here, maybe drifting in and out, and we've traveled an enormous distance together. We started in the late 1800s, when physics seemed almost finished, a few loose ends to tie up, and then the whole picture would be complete. And then Planck pulled on one of those loose ends, and the entire fabric unraveled. What emerged was something nobody expected, and nobody fully understands even now. A theory that tells us the world is not what it seems, that particles don't have definite properties until something interacts with them. Or maybe they do, but they're guided by invisible waves. Or maybe every possibility is real, in its own branch of an endlessly splitting universe. That the act of looking changes what you find. That two particles can be connected across the width of the cosmos in ways that Einstein called spooky, and that turned out to be even spookier than he feared. And yet this strange, counterintuitive, philosophically unsettling theory is also the most successful and precisely tested theory in the history of science. It explains why the sun shines, why matter is solid, why chemistry works, why your phone glows in your hand. Every transistor in every computer, every laser, every MRI machine, every LED, all of it rests on quantum mechanics. The theory works. It works beyond any reasonable expectation. It just refuses to tell us why. And maybe that's okay. Maybe that's even beautiful, in its way. We're a species that evolved to track prey across savannas and avoid predators in the dark. And somehow, improbably, we've managed to uncover the operating rules of reality at its most fundamental level. Rules that are nothing like our everyday experience. Rules that violate every intuition we have about how things should behave. And we did it not through revelation or pure thought, but through the messy, human, collaborative, competitive, sometimes petty, often glorious process of science. Real people, with real flaws, arguing in real rooms, scribbling equations on real blackboards, staying up too late, getting things wrong, trying again. Planck, who didn't believe his own hypothesis. Einstein, who started the revolution and then spent decades trying to undo it. Bohr, who built a kingdom of ideas and defended it fiercely. Heisenberg, brilliant and troubled. Schrödinger, with his cat and his wave equation and his complicated personal life. Dirac, quiet and precise. Feynman, irreverent and deep. Bell, working alone in the margins, asking the question everyone else had given up on. Aspect in his basement lab, proving that reality is stranger than anyone wanted it to be. And all the others, Born, Pauli, de Broglie, Bohm, Everett, Deutsch, Shor, Zeilinger, Bennett, Broussard, each one adding a piece to a puzzle that's still, beautifully, incomplete. That's the story. It doesn't have an ending, not really. The questions are still open. The experiments are still running. Somewhere right now, someone is cooling a quantum processor to near absolute zero. Someone is sending entangled photons through fiber optic cables under a city. Someone is working out the mathematics of a new interpretation. Someone is lying awake, much like you, turning these ideas over in their mind, wondering what it all means. The story continues. But you don't need to follow it any further tonight. You've come a long way. The ideas are in you now. settling in like light through water, and they'll still be there in the morning, waiting. So let them go for now. Let the particles do whatever they do when no one's watching. Let Schrödinger's cat sleep, and you sleep too.